having some trouble. It's not working anymore, and this is a common problem people are having with Skype. Um, also, if you can't hear me that well, let me know. I can switch to headphones and microphone or something. Okay, anyway, so yeah, download the PowerPoint and the whiteboard. That'd be the kind of thing where you'd probably just take some notes on that. I'm probably going to post those notes as well. It just kind of looks like this. I'll scan them and post them because the recording may or may not work. And then for the construction stuff, again, if you have the compass, I forgot to mention a protractor, or maybe I did, I can't remember, but a protractor would be useful as well. I'll be using those. If not, don't worry about it. It's just kind of a really neat way of doing optimization. Very different than anything we've done before, and very, very classical. I mean, it goes back hundreds of years, which is kind of cool. All right, so then I guess we'll get rolling then with the PowerPoint. But yeah, just someone speak up or text or something if you can't hear me, because I don't hear you guys, so it's like a little hard to tell. All right, so I'm going to go ahead and open up this PowerPoint. And I'm going to try to do it, instead of showing you the desktop, it's like Skype's able to directly link into the PowerPoint. And the nice thing there is because someone was doing this the other day in our capstone meeting, you can actually move back and forth. So if I'm going like too fast or something or too slow, you can just move through my deck. You don't have to wait for me. Okay, I'm just getting a little bit. Let's do this gallery, content view. Okay, there we go. All right, so we're going to be talking about Steiner trees today. So what are Steiner trees? So you can start off with this situation where you have a bunch of nodes, a bunch of locations, and you want to connect them all in a tree, just like a minimal spanning tree. This is actually a map of the vicinity of Stowe, Vermont. And let's say these are a bunch of recreational sites that we wanted to connect with some trails or some roads or something like that, where you can get from any one of them, any site to any other site. So the solution here, if you look kind of closely at it, you'll see that it has these, what you might call degree 3 junctions. These are spots. These weren't actual nodes or vertices in the original problem. Okay, I'll click again. You see these white nodes come in. And so the idea here is we've actually added vertices to the problem that don't need to be connected, but by including them, they can actually reduce the cost of the overall spanning tree. Okay, and I'll show a bunch of examples of that, but that's the essential of the Steiner tree problem. The essential point of it, it's trying to solve the minimal spanning tree problem with the addition that you can use extra points. Turns out that it ends up making solving it a bit more complicated. All right, so to frame it, you can start with the minimal spanning tree problem. It's weird, it just told me the recording is ready, which is weird, unless I stopped recording. No, okay. Anyway, and we've seen this before, so we did this last class, I think, or 2 classes ago. A weighted graph is what we start with, and we want to find a spanning tree that connects all the arcs. Connects all the nodes, and we want the one that has the minimal cost, and that's known as a minimal spanning tree. So the Steiner tree problem, what if we're allowed to use additional nodes to help reduce the tree cost? So suppose we could add this node here, this 4 node, in the center. Didn't need to be connected, but if adding it reduces the overall cost of connecting the 3, then let's do that, at least according to the Steiner tree problem. We're allowed to. And so this is a sort of simple example, but in this particular case, we're able to reduce the cost of the tree from 4 to 3 while everything is still being reached. We do have to add this 4th node here. We generally assume that there's no cost to adding that node, although there are variations on the problem where there might be one. This problem, we're going to look at the geometry of this near the end. That's where the compass is going to come in. For now, though, we're just talking about this as a weighted graph. Okay, so here's the setup of the Steiner tree problem. What we have is a set of terminal nodes. So the original nodes, the original vertices that we had in the problem that we wanted to connect, we kind of give them a slightly different name here. We start to call them the terminal nodes. That's to distinguish them from these additional extra nodes that we can use if we want to, but that don't have to be in the network. Those are called the Steiner nodes. So we're given that, and we're given all the arc information. How much does it cost to connect any node to any other node? And again, the goal is to connect all of these in a tree, minimizing the total cost. Okay, and there you go again. Additional nodes, Steiner nodes can be used to help minimize the tree cost. So that's the basic problem. So it turns out this is actually harder to solve than the minimal spanning tree problem. And so the question is why? Now you could click ahead on the slide, but this is a point where I would open this up to the class. So does anybody have any thoughts on why this is actually harder than the original minimal spanning tree problem? Whoa. It looks like Tommy Klawitsky, you were talking, but your voice came through in sort of like chipmunk style.
Tommy sounds like Alvin and the Chipmunks.
Yeah, you sound like a chipmunk. That's so weird. Something must be wrong with your connection or mine. You could type it in the text or you could try talking again. Yeah, I mean the chat. That's what I meant. Are you guys also hearing him like that? He sounds like a chipmunk. That's weird.
Yeah, we're hearing it like that.
Okay. Okay, so while people are typing, if anyone else can think of it, you can type it in the chat as well. Why this is harder.
Is it harder to solve just because you have to use the computational effort to make another node if needed?
Not exactly. It's not, making those nodes doesn't cost you very much. Or let's say making one node like that doesn't cost much. Making 2 or 3 doesn't either. If I go back a bunch of slides, see, these examples are kind of easy because it's somewhat intuitive where you would put the Steiner node. This one, let's back all the way up to here, okay? Okay, so Abby says, is it trying to weigh if adding the node actually makes a positive impact? Okay, so yeah, you're on the right track. You said adding the node actually makes a positive impact and is worth it. And Tommy Klinsky, you need to create new information. You aren't just using the old. Yeah, so you guys are all kind of hitting on it. The way I would say it is the original problem, you know exactly where the nodes are. With the Steiner tree problem, typically, you're not necessarily, it's not proscribed, it's not told to use these Steiner nodes. It might be in some cases, but like in this Stowe, Vermont problem, we don't know where they are. And we have a lot of choices as to where to put them. We have a lot of choices. So how do we decide? And so I'll go back up and you'll see the rest of this slide. So how many Steiner nodes, if any, do we use? Suppose we had 5 Steiner nodes. Let's say we were given, they said, okay, here are 5 of them that you can use. Right away, we have 32 possible sets of Steiner nodes we could use, right? Because that's how you do that. If you have 5 choices, either use or don't use, you end up getting to the 5th choices. So now I'm looking at 32 possible trees. So to solve it, what you could do is you could say, okay, I'm not going to use any. Let me find the minimal spanning tree. Okay, I'm going to just use the first Steiner node. Let me find that minimal spanning tree. Now I'm only going to use the second one. Find that tree. Now I'm going to use the first and second. So you find the tree for all of these, and then you get 32 different trees. Again, these are minimal spanning trees. We're saying that node's definitely going to be included. Looks like my screen just disappeared. Okay, throw that back up. I don't know why it disappeared, but try that again. Anyway, you have all these various choices. And so searching through all of them, if they're small, is no problem. But if you have a lot of Steiner nodes, then it's a problem. Okay, I think I got the screen back up. Hopefully you guys can see that. So here's on this next slide, if the number of Steiner nodes is large, an exhaustive search, like going through all the 32 in the last case, that's going to be slow. So if we had 10 choices of Steiner nodes, we're talking about 1,000 trees to sift through. We had 50 nodes, and you could imagine 50 nodes in a problem, a big problem with a lot of nodes to connect. Now we're getting into like, age of the universe size numbers, and 100, forget about it. So we start to get into, as you guys hopefully remember, the computational complexity issues with this. It's a common situation in a lot of optimization problems. In practice, right, what we would do is use an algorithm that can quickly approximate the optimal solution. Quick quiz-like question. What are those kind of algorithms called again? Quickly find close to optimal solutions. Nice, that was quick. Heuristics. All right, Justin hit the buzzer first, it looks like. Yeah, so you definitely want to remember that word, heuristics. It's definitely one thing I'd love for you to leave this class remembering. Okay, so what I'm going to do for the remainder of these slides, there's a few different things. I'm going to spend some time talking about some variations on this problem, and I'm also going to dive in a little bit into some work that I did in grad school on this, just to show you an application. The specific stuff I did in grad school is not going to be anything I'm requiring, just kind of sets up the environment and how the Steiner tree fits in, some applications of it. A little bit later on, I'm going to get into the specific version of the problem, the Euclidean problem. It's a very common one. Okay, and we'll do some mechanics. We'll do some math actually on it, involving gradients. A nice little review of some multi-concepts that will kind of help prep us a little bit for when we get to nonlinear optimization, some of those same techniques. So there's kind of two reasons for that showing up. All right, anyway, these are a bunch of variations. So the problem in networks, the Euclidean Steiner tree, I'll get to that later. It just means the points are located in physical Euclidean, usually two-dimensional space. So the weight between the arcs, the weight between the nodes is simply the Euclidean distance. You can do the same thing in 3D. There's a so-called rectilinear problem. I'll show you a slide of that. And then this Euclidean non-uniform, that's a problem that I worked on a bit in grad school. In fact, when I came, some of the slides I'm showing you have been recycled from when I applied for this job and I came here and did my job talk. I spent some time talking about that because that was the most OR, operations research OR, part of my thesis. All right, here's the rectilinear. This is a very applied problem. Any of you guys have any experience in electronics, like circuit design, that kind of thing, even some soldering of circuits to a circuit board, or anyone who's ever really opened up a piece of electronics like a computer? You might have noticed the circuit boards tend to have these connections. They have these like components on them with these connections, and the connections are linked to each other, like a resistor to a microchip or something, with these usually these sort of lines of conductive. I think it's some form of solder, or not solder, but some sort of wire, but it's essentially etched on or painted on. Anyway, you have all these components and you want to connect them in a particular way. So how do you do that in a way that minimizes the amount of this wire material that has to be laid down? Okay. And so what ends up happening with these is sometimes you might have a little junction like right over here. Can you see my cursor, by the way, when I'm moving the arrow?
I can't see your cursor.
You said can or cannot? Oh, you cannot.
I cannot see your cursor.
Okay, that's a bummer. Must be because I'm doing it in the presentation mode. I don't think there's a way around that here. All right. I think I'm going to leave it like that. So basically what I'm pointing at is if you look kind of in the middle. Oh, there's your cursor. How'd you do that?
Doctor, there's an edit tool with a laser pointer in the top right hand corner. At least I have a top right hand corner of the slide.
Oh, there we go. Oh yeah, perfect. Thank you. Man, you always find good stuff. Okay, here's the little laser pointer. Oh, let's try that. Yeah. Okay. Great. Thanks, Jacob. So right around here, you've got a little junction. In other words, you would put something here and it would connect to this and connect to this and connect to this as well. So we would have a new node, Steiner node right there. Okay, so here's another version of it. This is actually a biologically inspired one. This is a 3D Steiner tree problem where we've got these various molecules in the helix, or in the helix of DNA, that kind of thing. And it turns out some of the solutions to these naturally satisfy Steiner tree properties. In other words, you find these components in here that serve a structural purpose, and they create a network that has the smallest amount of connections that it possibly could. They just land where the Steiner tree problem solutions would suggest that they would land. So that's pretty neat. Um, okay, so this is a problem that I worked on. So here you have a bunch of nodes, except they're located on some uneven landscape, and you want to connect them. But now the connections have some price to pay depending on where they go through. So for example, I've got a node over here, and I've got a node over here. But if I wanted to connect these two, I have to kind of go through the mountain or up and over the mountain. That's more costly than going around the mountain like this. So you can imagine each one of these cells has a cost. And you could think of that cost as a cost to lay cable or lay tracks or something through it. So that's what this problem is. It's located in a physical space, except it's more than that. Each physical cell has some cost associated with it. And I'll give you an example of this later, where the cell cost depends on things like the elevation of the cell, the slope of the cell, maybe the type of land that's there. If it's wetlands, maybe you have to go around it, that kind of thing. And this is work that I did with my advisor at the time, Bruce Golden at Maryland. Okay, so I talked a little bit about this already. The implementation of this, the methodology, we ended up in order to, I was talking before about where are the Steiner nodes and how many of them do you use. So one thing that's typically done is you convert the space into this hexagonal lattice, and then each cell on the each hexagon has a cost associated with it. So in this particular problem, I'm trying to connect these black dots on this landscape in the minimal cost fashion, where the cost depends on the color of the cell. Blue is cheaper. The red is the most expensive. And there are a bunch of applications here: cable networks, transmission lines, printed circuits. So it's very similar to some of the applications I showed earlier. Okay, so I'm not going to show like much of the details. One of the ways we solved this was with the genetic algorithm. It's the methodology. Not really, a little bit beyond the scope of this class, but the problem itself fits in nicely in the scope of this class. But these are some results. So here's a typical example where you're trying to connect these nodes. The nodes are the original terminal nodes are the black circles. And the Steiner nodes, you can kind of ignore these red triangles. They're sort of an artifact of the hexagon. These would be replaced by straight lines, straight edges. But the little orange stars indicate the Steiner nodes. So you can see like what's happening, what it's trying to do is it needs to connect this really costly node in the middle here. And it does so by sort of reaching in. It just does this little diversion from the outside into the middle like that. Okay. And you see another one over here. Sorry, let's get my pointer on. There we go. This is what I was talking about. So there's a Steiner node there, and there's another one over there, right? What I'm doing here is I'm actually comparing to the optimal solution. This problem was small enough that I could do the thing I was talking about before. I actually went through all the possible solutions. It took a long time. And here's my solution, which was a heuristic. So not optimal, close to optimal, and much, much faster. So this was kind of the essence of this portion of my thesis: develop a heuristic to solve this particular problem. Okay, so a little bit after that, what I did is I wanted to come up with an application of it. So this is where I started off talking about linking up recreational sites in Stowe, Vermont. And what I ended up using on this was GIS. I don't know, maybe some of you are familiar with that. We have a GIS course here. I think there may be more than one that a lot of orcas take as an elective. It's offered by the MES department. Anyway, I view it as kind of like a computerized geography. It combines data and hardware and software. It's kind of like overlap a little bit with the data side of data science. And you end up working with these layers of GIS data, geographic information system data. So I did an application in that. In fact, I think when I first started here, there was a GIS training that I went to just out of curiosity, and that led me to this. All right, so in connecting these, we have some considerations, right? In these models, we always do. Suppose that we want to connect these recreation sites where we prefer the connections, the links, to be, number one, at low elevations. Number two, we want them to be relatively flat. And number three, we want them to satisfy certain land use preferences. So, for example, we might want to avoid wetlands, and we might want to go through forests as opposed to farmland, that type of thing. Okay, so in the GIS, and so again, I'm kind of like digressing a little bit from the main focus of our OR major to show you like you have these considerations, and you go out into this GIS world to help you kind of prep your data, right? So it's a little bit of a outside education that you can get to help you get data that you can then use to help you solve your problem. So I went into this program called ArcMap, and I loaded in data, geographic data, of these various layers. I'll talk about some of these in a minute, but some of them are probably logical. So the first one in there is the recreational sites. So that's just like the lat and long of these sites. So I can load those in no problem, and once I have the data, it's pretty easy to get it in. I think the other one that I used here was land use. So again, just some other data set that I was able to find for this area. And you can see it's color-coded by the type of land. So for instance, yellow is agriculture, this lightish green is wetlands. And again, these are going to be turned into numbers where the numbers are such that if it's not a good place to be putting a road through, then the number should be high. It should be costly. Okay. Any questions on that so far? Okay, just shout out if you have one. Here's the elevation layer, so this is how high things are. And again, we wanted these trails. Again, that's just our concern in this one. Let's keep these things low if we can. You could have all different other kinds of considerations, but that happened to be ours here. So whatever, if you want an elevation concern, you need the elevation data in there. So there it is. And this one's kind of interesting, the slope, because unlike the elevation, so the elevation we just get data. There's like some sort of matrix that says at this lat and this long, here's the elevation. We don't have that for the slope, at least I didn't have that initially, but that's no problem because if you have the elevation data, then you can generate the slope data. Right? So you can think about that for a second, but hopefully that's clear. If all I have is elevation data, I can just generate the slope data. So you're just looking at the change between one cell from one cell to the next, divided by the spacing of the cells. It's in a way, you're kind of like taking the derivative of the whole data set. All right, so with those various inputs, the land use, the slope, and the elevation, I combine them. This is just like a block diagram showing how these things all get combined. And then weight it. So you can weight them in different ways. It kind of reminds us of the goal program where we could weight various goals in different ways. Essentially, I'm creating a cost structure that's going to weight these various inputs in whatever ways I want or the decision maker wants. So with these various weights, they all get reclassified. That just means we want to put all the numbers on the same scale. And then I called it Ian grid at the time, but basically those are my final numbers, and they look like this. So this color-coded scheme here represents how costly it is to build a connection between a given cell, okay, a given location, which again factored in those three things: the land use, elevation, and slope. Okay, so with that, now we're actually ready to solve this thing as a Steiner tree problem or as a minimal spanning tree problem. Okay, but again, in our case, we're doing Steiner tree. This slide just shows a little bit of my workflow. Not really that important for us. Just did some stuff in ArcMap, GIS. I did everything in MATLAB at the time. So I ran all my calculations in MATLAB, did the math in MATLAB, and then I sent it back into ArcMap. There's probably a way to run all this through ArcMap by writing this in C++ or something and calling it that way. Anyway, what's important, I guess, what's important is that the data gets input on this end, the terminal nodes and the grid cell costs, and what gets what gets output, that's input, are the Steiner nodes and the tree cost. Okay, so it's like, where should you put these junctions, these special Steiner nodes? And this is just showing a solution to that. This was actually shown earlier, but you can see it adds some Steiner nodes basically in a few of these spots just to help reduce the cost of it. Okay, so just kind of a proof of concept of saying, hey, we could solve this problem with real world data. Now, funny thing happened after I did this. I presented this at a conference and it was posted online. Didn't really get much attention or anything. But one day I got an email from a computational archaeologist in the Netherlands, and he was researching reconstruction of ancient Roman roads. So Philip Verhagen and his colleague Sylvia Pola asked me if my algorithm might be suitable for what they were trying to do. They had done all this prior work trying to reconstruct these roads, studying movement practices of ancient peoples and whatnot. And they had this data, I think this was from Turkey somewhere. So they had these various sites and these various trails, and they wanted to know what would happen if we tried to connect these things in a network of trails, like basically a minimal spanning tree or a Steiner tree, factoring in, again, the land use, elevation, some of the considerations I had. So yeah, so we did that. So they sent me data, and I ran the algorithm on it, and the yellow is the output. These were some other calculations or other archaeological finds about roads, and so in some cases it was actually quite close. Mine's a bit more jagged again because of the hexagon, and I probably should have smoothed these out before putting them in the picture, looking back on it, but you can just imagine these zigs just being replaced by smoother lines or straight lines even. But you can see that it generally traces over other paths, and it also suggests the location of junctions. So Steiner nodes here, okay, these various spots. So that was kind of fun and interesting. Okay, so that ends sort of the survey of Steiner trees. We're going to spend the rest of our time primarily looking at this specific problem, this Euclidean Steiner tree problem, because it's got a lot of nice, good math in it. The Euclidean Steiner tree problem is set up very simply. The nodes reside in Euclidean space. Okay, so just some points on the plane. The arc weights are simply the Euclidean distances between the nodes. So in this sketch, we were given, let's say, these 3 red nodes, and our goal was to find a Steiner tree, a Steiner node that would link the red nodes in a minimal cost network. And so that's reminiscent of this picture that is showed on the earlier slide. Okay. Any questions? Does that make sense? Like what this problem is trying to find? Okay, thanks. Got one yes. Okay, good. So I don't know, by the way, if my video is on or not. It probably doesn't need to be, but as long as you guys can see the slides, I'm good. All right, so there's a neat history to this. I just have a little bit on this one of the Euclidean Steiner tree problem. So sometimes these Steiner nodes are called Fermat points after the mathematician Fermat. And also called a Torricelli or Fermat-Torricelli point. And that's just defined as if you had 3 vertices of a triangle, it minimizes the distance from that point, the sum of the distances from that point to each of the other 3 points. So it's named that because Fermat raised the problem and supposedly Torricelli answered it in a letter to him. And I don't remember the dates on this, I think 1700s. But what's cool is that this can be found by construction, and this is what we're going to do with the compass and protractor. So again, I want to emphasize that this is like a really unusual case for us in optimization. We're going to solve an optimization just with straight edge and compass and some math principles underlying that. The Wikipedia page is good on this if you want to look at that. I believe in the homework, if you don't have a compass, I asked you to solve one of these with a compass on the homework. If you don't have one, I think I gave you the option of reading a Wikipedia page. I think it was either this one or the other, or the Steiner tree one. So here's how it works. We're gonna do this not quite immediately. We'll do this a little bit later on today. One other thing in between. But the way that you do this is if you go back to Torricelli's original quote. Oh, I'm sorry, I had the years wrong. It was 1600s. And what he said is the 3 circles circumscribing the equilateral triangles constructed on the sides and outside the given triangle ABC intersect at the Steiner node. So that's kind of a mouthful, but if you go back here to this picture, we're doing a bigger one. Yeah, this bigger picture here. What it's saying is draw equilateral triangles off of each of the sides of the original triangle. Okay, so there's one equilateral triangle. There's another. Then circumscribe them. That means enclose them in a circle. Okay, and the marks are kind of light here, but the location where those 3 circles intersect, that's the Steiner node. Okay. So it's pretty neat just drawing those constructions. You can find it that way, and you can prove why that's the case as well. So we're going to follow a method along these lines. We'll construct an equilateral triangle. You can actually shortcut the method a little bit by only doing it on 2 of the sides. Then we'll circumscribe those 2 sides, and then the 2 circles will intersect at the Fermat point, aka the Steiner node. You could do the 3rd circle off of the 3rd triangle, off of the 3rd side as a check if you wanted to. Okay, so that's the plan for the latter part when we get to the mapping or the compass and protractor. But before we do that, we're actually going to do mathematical proof that the angles of each pair of line segments from the Steiner tree to the terminal node are 120 degrees. So like this over here, this is a line segment from the Steiner node to the terminal node, okay? And so is this. The angle between the neighboring ones is always 120 degrees. And you might have kind of seen that, it might have looked like that in the pictures that I have. Always 120 degree angles, okay? And so we're about to prove that. All right, so yeah, just shout out if you have a question or throw something in the text. What I'm going to do now is I'm going to switch over to the stylus and the notebook, and I hope this will be relatively clear. I think I'll scan the notes anyway and post them if it's not. I haven't done one very long like this before, so we'll see how this goes. All right, so I'm going to switch from the slides to monitor 3, which is where my tablet is. So you should be seeing that soon. Okay, so it's telling me that you're seeing that. That's good. All right, so I'm going to do a decent amount of writing here. This is just going to be like more of a chalk talk type thing that we've seen, you know, like in more of like a standard math class. So, all right, so I'm going to set up this entire problem. I mean, what you want to be thinking about in the back of your mind for all this is I've got the 3 original nodes in here, and then I've got a Steiner node that I'm going to make a tree out of, and that's going to connect these guys. And what we're after here is that this angle is 120 degrees. Okay? Is that legible? Can you guys make that picture out okay? Yes, yes. Awesome. Thank you. Thank you. Okay, great. So again, I'll write up a bunch of stuff now. So we're going to be given 3 distinct non-collinear points. What does non-collinear mean? Not on the same line. Yes, thanks, Justin. That's right. Otherwise, this problem would be kind of a little pointless. But in any case, in the plane, okay, so we're only going to do stuff in 2D. And there's one other little stipulation. If you read the Wikipedia page, it's got more info on this. You don't have to worry about this too much. We're going to assume the triangle ABC has no angle greater than 2 pi over 3, which is 120 degrees. Okay, so we don't have any extremely obtuse angles in this triangle. If you do, it ends up being a little bit simpler, so we're just going to not worry about that case too much. Okay, so given all that, we're going to find a point, we'll call it P, in the plane. We'll call it a Steiner node. And we're going to hear back from Justin Steiner if there's any relation there. I wouldn't be surprised. Anyway, such that, oops, and I just changed color by accident. All right. Not that there's anything wrong with that, but such that. So we want to minimize the distance, right? If I go back up to the little picture, we want to minimize this total amount of distance in here. So let me actually label these. So there's A, there's B, and there's C, and that's P. So I want AP plus BP plus CP. I want those 3 lengths to be minimized, okay? So that's how I'm going to write it, just denoting length with the absolute value bars, which is frequently done. AP plus BP plus CP, those lengths is minimized. Okay, just anybody stop me if something's not clear, either idea-wise or visibility-wise. Okay, so we'll move ahead. Whoops, we'll move ahead now with our solution to this. And the solution's broken up, just to give you a heads up as to how long this is going to take. There are 4 parts, okay, 4 parts to it. A, B, C, and D. I'm not going to spend much time really in discovery mode, like why would we think to do this? Whoops. just because I think that would take a long time to do. Okay, I'd encourage you to do it on your own, but this is going to serve as we'll get the proof knocked out and also some nice review of some techniques that will come in handy once we get to nonlinear. All right, so let's define the coordinates of the various points. So the coordinates of points, let the coordinates of the points be, for A, we'll just call it x1 and y1. For B, we'll call it x2 and y2. And for C, we'll call it x3 and y3. Okay. Oops, that's... it does not want to get rid of that C here. Let's get rid of that guy. Okay. Okay, there we go. All right, now this is going to be important. This next symbol, I'm going to let D1. Okay, these are going to be really important. D1 is going to be a function of x and y. It's simply going to be the distance between A and P. Okay, D1 is the distance between A and P. So I think I don't want to throw you off too much by scrolling back up, but you remember the picture looked like this. There's B and there's C. So this distance here is D1. Okay? That's all. And we'll have a similar D2 and D3, except we're not going to do any math on those because it's going to work exactly the same as the math on D1. So, all right, so here's where we get into some fun multi. And I actually found this problem in a multi-book, or this proof, I should say, in a multi-book. We're going to start off by computing the gradient of D1. I like how it changed my little gradient into a nicely drawn gradient symbol. Okay, so we're going to compute the gradient of D1. When we do that, what we're also going to do is we're going to show that it's a unit vector. Okay, so remember what a unit vector is. Remember how you would show that a vector is a unit vector. We also want to show that it's in the direction from A to P. Okay, so we will do all that now. Okay, so to do that, let's actually start off before we compute the gradient of D1. Let's just write out what D1 is. Anyone want to chime in? It might be a little hard to throw it in the chat. I suppose you could. What's the formula for D1? Because I've defined, right? I defined all the. Oh, I forgot to define 1 point. Sorry. Let me just pop back up here. When I said C was x, had the points x3, y3. I also want to define that P has the coordinates. I'm sorry, x and y. Okay. So if you missed that, I just forgot to put that in there. Okay. With that, can anybody tell us what D1's formula should be? Or even in English-ish kind of terms, how that would work. Yeah, nice. Okay, Justin just threw that in the chat. Yeah. Right, so distance formula, again, it's our square root of the sum of the differences of the components squared. So in this case, this is why as I was thinking of the formula, I realized I forgot to put P in there, so we do x minus x1 squared plus y minus y1 squared. Okay, good. All right, so maybe that's basic. I don't know. Yeah, I'm just checking mine with yours. Okay, I'm just going to write that. Well, I guess you could write that as that whole thing to the 1/2 power if we want. Reason being is ultimately I want to take derivatives of this. So the gradient of D1 now. So how do we compute a gradient? Right? Do you guys all remember how to do that? What's the gradient? So I'm going to use these as the vector symbols. So the gradient would just be like the partial of D1 with respect to x. So we would take the derivative of that function with respect to x, and then its second component would be dd1, so the partial with respect to y, like that. Okay, and so this is going to get a little bit messy here, but it'll clean up a little bit. If you take these derivatives, so again, maybe I should have written it. Let me just go back up here for a sec. This part would have been like x minus x1 squared plus y minus y1 squared, all that to the 1/2, okay? So now when I take derivatives, they look like this: 1/2 times the quantity x minus x1 squared plus y minus y1 squared, all that to, now the power goes down, it was 1/2, so it becomes a minus 1/2, like that. Furthermore, right, because it's a composite function, so the chain rule is in effect. So I'm going to get a 2 times x minus x1. And then there's another chain rule off of that. Oh, did I do this backwards? Let's see, x1. Okay, this one doesn't have it, so that's fine. In my notes, I had it reversed, but that's okay. All right, so that's our first component. If I got that one right, just looking it over myself here. Okay, I think that looks good. And then you get the same idea for the other one. It's just 1/2 times, for the y component, the y derivative, x minus x1 quantity squared plus y minus y1 squared to the minus 1/2. Only difference here being, right, so Blue's Clues moment, you just would fill this into y minus y1, like that. Okay, so that's D1. Let's simplify. Sorry, that's the gradient of D1. Let's simplify that a little bit. What it boils down to is I can just, they both have these same terms of 1 over the square root of x minus x1 squared plus y minus y1 squared. So I'm just going to factor that out completely from the vector. Right, see what all else happens? The 1/2 and the 2's cancel. And then on the inside, I get these components, x minus x1 comma y minus y1, like that. But what do you notice about this? We can simplify this quite a bit more. And I'll just sort of suggest by how much we can simplify with the amount of room I'm leaving for that denominator. Anyone want to shout out what goes there or pop it in the... Yeah, this is 1 over D1, so you just need D1, right? Because this, let's go like that. Like this guy over here, that's just D1. Okay. So that's simplified that nicely. And all right, so what are we doing again? So we had to compute, D1 and show that it's a unit vector, and also that it goes from A to P. So we computed D1. Now let's do the part about showing it's a unit vector. How do you show something as a unit vector? You guys just, again, be answering this in your mind, or you can shout it out loud. You want to show that the norm or the magnitude of it is equal to 1. So what does that look like here? Again, just doing some math on this. You just would square each component and then add them. So I have x minus x1 squared. I'll just put the D1 squared in there like that. We could have kept it outside. It might have been better, but in any case, too late. So I get that. And so each term has a D1 squared in it. So yeah, maybe I really that was dumb. But in any case, let's just pull that all the way out. I've got 1 over D1, right? Because I could factor it out at each term. And then that's times the square root of x minus x1 squared plus y minus y1 squared. Okay, but that's simply D1 as well, right? That's 1 over D1 times D1. And so that's 1. So, yeah, so the gradient of D1 is a unit vector. All right, trying to get too fancy here, I guess. There we go. All right, so that's the first thing that we had to do, right? The other thing we had to do is to show that it goes from A to P. And this is all still part A, so it's getting a little bit long. But the other parts actually collapse a lot more easily. Yeah.
Doctor, why is that 1 over d1 times d1? Because isn't that the square root of d1?
Uh,
Oh, never mind. That is d1.
yep.
Okay. I
Yeah,
see what.
this quantity over here is
Okay.
d1. Yep. Okay. So now let's show that let's show that it goes from A to P. This is again more, to my mind, this is more good multi-review, that could come in handy for, that could come in handy for the nonlinear optimization that we're going to be doing. So let's put it this way. Let's say that the line from A, which remember has coordinates x1, y1, to P, which has coordinates xy, is given by. So I don't know if you guys remember how you describe lines in 3 space, right? So you can think about that. How does that work again? You definitely want to try to have that handy, or if not, just kind of load that back in. There are different ways to do it, but typically a line in 3 space is specified with parametric equations, okay? And so the idea behind it, I'll sketch a little bit over here and then I'll write the formulas. So here's A, which is x1, y1, and here's P, which is xy. And so if I want to characterize this line, okay, I want to have like some parameter t that tells me where on the line I am. And I also want to say, and there's missing a comma here, I also want to say I'm starting off, my x-coordinate starts at x1, and my y starts at y1, and then I'm going to have a t which tells me how far away from that starting point I am. And then that t is going to be multiplied by some direction. So I don't know if this rings any bells. We cover this kind of thing in multi. So there's a vector that's pointing in the same direction as AP, and the components of that vector are, anyone want to take a guess? Or what are the components of the vector pointing in the direction A to P, given these coordinates here? So what goes in here? Yeah, good, Jacob. X minus x1 and then y minus y1. Okay, so that's exactly what we'll plug in here. If it's, maybe this is very familiar, but if it's not, just spend a little bit of time looking this over and thinking about it. T is this sort of parameter, tells you where on the line you're at. So when t is 0, you're at A. When t is larger, let's see, what would it have to be? 1. When t is 1, then we are at P. So basically, t taking on values between 0 and 1 puts you between A and P. And greater than 1 puts you beyond P. Less than 0 puts you before A. All right. Let's write this, or let's rewrite this in vector form. So now what we're saying is that x1, that this can be written as x1, y1, the vector, or the point, really, plus my stylus stopped working. Okay. So I just twist the top off and twist it back on. That's been working for a while, but we've been stocking up on, what are they, quadruple A batteries in the department now that we need to use these. Okay, I totally forgot what we were doing. So, okay, I'm back. T times the vector x minus x1 comma y minus y1. Okay. And so if you go back and you looked at D1, right? Remember what the gradient of D1 was. So recall, gradient of D1 was 1 over D1, and then it was just x minus x1, right, comma y minus y1. So now you compare these two, and you can see that they have the same vector, right? In other words, D1 has this direction for it, and the line AP has that direction for it. So that shows that the gradient of D1 points along the line from A to P. Okay, so again, these match. I'll just say directions match. Okay, so that concludes A. Just can kind of see how long that was. Oh wow, I got a lot wider. Sorry about that. This is going to be a learning process. I was trying to like not get wider, but I did. Oh well. There's probably a way to safeguard against that, so I guess I could draw some lines or something. All right, anyway, let's move on then. So B, I'm not going to write all this out, but what you have would be similarly, you could do the same things for B, whose coordinates were x2, y2, and C, is that green again, C, whose coordinates were x3, y3. It's not like the thickness there. All right. Okay, so all you would have to do is replacing all the ones in part A with 2 and 3 respectively. So that's how you would do it. So what you then find, right, you just want to make the analogous conclusions now about the gradient of D2. It is a unit vector in the direction of the line from B to P. Okay, so it's a unit vector in the direction of the line from B to P. I'm going to say the same exact thing for the gradient of D3, except C to P, like that. Okay, so that takes care of part B of this process. And so let's move on to part C. Again, there's only 4 parts, so we're getting there. This is kind of the key part here, where we get into the optimization. This is probably the most important part. The rest of it was kind of set up. So let's create a function f that represents the quantity that we're trying to minimize. Okay, f is going to stand for the quantity that we want to minimize. So what's the formula for that? This is simple, just to make sure you guys are tracking. What's f of xy supposed to equal? You said question mark. So I'm asking, remember what we want to minimize here, right? And f is going to stand for the thing we're going to minimize. So we're trying to basically minimize, the lengths of these guys. So f should represent the lengths of them. But we've defined a bunch of quantities already that we can use to plug in for this formula. Anybody? What's f in terms of our quantities that we have already? Huh, okay. I just mean D1 plus D2 plus D3, right? Because D1 was just the distance, right, from A to P. There's A. And then D2 is to B, and D3 was to C. Okay? Make sense? That's what we want to minimize. Okay, good. Okay, good, thank you. So, all right. Now we're going to leverage a little bit of optimization that we know about from Nano and elsewhere, maybe even multi. So if f has a min at xy, there's a little bit of like kind of existential stuff going on here. Like we just presume that it does. Looking at the problem, it makes sense. It stands to reason that it should. There should be some point in there that has the lowest amount of value. It's not like unbounded, for example, unbounded below. So there should be a min. So if that's the case, though, when you have a min, right, that means that we would have the condition where it's sort of like in one variable, there'd be the first derivative would be 0, right? So remember the condition in more than one variable. We have that the first partials are 0, so we have And this is notation, hopefully you guys remember this, f sub x, that means the partial of f with respect to x, right? That's equal to 0, and the partial of f with respect to y is also equal to 0. Okay, so that would be the case if we have a min. Now, what we want to do is we're going to say, all right, yeah, let's assume we have the min, so we're going to assume that we have that f of x, y, fx and fy being 0. What we're going to show in this part of the problem is that if that holds, right, so this part where we get these two partials being 0, if those two things hold, what we want to show in this part, is that the, hang on a sec, let's get rid of this guy, show that this quantity, the sum of these gradients, gradient of d1 plus gradient of d2 plus gradient of d3, show that that's equal to 0. Okay, so that's our task here. So we're going to work with this sum of gradients and show that that sum of gradients ends up equaling 0, assuming that we're at the min. So it's like you're somewhere inside the triangle, right? You're computing these gradients. The gradients are giving you an indication of how quickly the distance to the point is changing. And at the min, what's supposed to happen according to this part is that the sum of those gradients ends up being 0. So let's see how that works. So I'm going to rewrite this. So, or equivalently, I'm just going to plug in the formulas for the gradients. So the gradient of d1 is just the partial of d1 with respect to x, comma, the partial of d1 with respect to y. So that's the gradient of d1. And then you just write the similar terms for the other two d's. So partial d2 with respect to x, comma, partial d2 with respect to y. And finally, partial d3 with respect to x plus partial d, not plus, comma, partial d3 with respect to y. Okay, so that's just it spelled out, the gradient's spelled out in component form. All right, a bit more writing on my part. If you want, you could skip this step, but I'm just going to consolidate these three vectors into one vector, right? I can just component-wise add them. So I get dd1 dx, these are all the first components, plus dd2 dx, plus dd3 dx. That's the first components summed. Likewise, I'm going to do the same thing for the y. So dd1 dy plus dd2 dy plus dd3 dy. Okay, so just a little rearrangement going on. But now it collapses. Into what? So what's that first term? What's another name, another way to write that first term? Got to dig back into the multi for this. Oh, somebody's typing. Some people are typing. Good. Yeah, well, that's what I'm asking, right? The sum of all the partials with respect to x. That's right. And so what's a compact way to write that? Two people are typing. Greek letter F, I, There's definitely F is part of the answer I'm looking for. So if I go back up to f, and I were to take the partial of f with respect to x, right? Look at this f up here. Yeah, okay, Jacob, you just said it. Good. Yep, so that's just the partial of f with respect to x. In other words, look at f. Let me highlight it for you. So, oops, got a really thin marker here, but whatever. That's my f function. And if I take the partial of that with respect to x, so I'll just use that notation, fx, fy. Okay, but that's equal to, as you guys might have noticed from up at the top here, that's just going to be 0, 0. And so what we end up with is that this is the 0 vector. Okay, so that's what we wanted to show. So this sum of the gradients ends up equaling 0, the 0 vector. Okay, so that's the key for part C, which leads us to our last part, which is D. And this is where everything kind of comes together. Okay, so here's D. So I hope this is readable on here. I mean, I don't think I've ever taught like this before. So anyway, so the vectors, so what we have here is that these are vectors, right? These gradient vectors, gradient D1, gradient D2, and gradient D3. So we've just shown that these guys sum to 0. Let's be zoomed in or something, but anyway, sum to 0. All right, so we can rearrange this a little bit. We can say that the gradient of D1 plus the gradient of D2 is equal to minus the gradient of D3. Okay, I'm going to square both sides. So again, when I was talking earlier about how is this discoverable, not sure why you would think to do this, to be honest, right? You'd want to just spend a little time thinking about, why might this make sense to do? I think it has to do with the dot product, though, so that might give you some rationale for it. In any case, I'm just going to go gradient D1 plus gradient D2 times gradient D1 plus gradient D2 on this side. Whoops. Okay, and then on the other side, I just get minus gradient D3 squared, which just gives me gradient D3, the quantity, squared, like that. All right, I'm going to expand this side, or FOIL it. So D1, gradient D1 squared, plus 2 times gradient D1, gradient D2, plus gradient D2 squared equals gradient D2 squared. All right, it looks like this looks wrong here. This is a... that was supposed to be a 2. So I think it auto-corrected that into a 3 or something. I don't know what's going on there, but I'm just going to write over that.
Doctor, why would that not be a 3 from the equation I have above?
Oh, yeah, what am I thinking? I wrote the 3. Thank you, sorry about that. Yeah, that was a 3. Okay. And so this one's a 3 too. Jeez. All right. Thank you. So yeah, let's fix that. So this is still 3. Okay. Thanks for catching that. Okay, so that's D3 quantity squared still. All right, so then we get some simplifications. Anybody know a quick simplification on here? On the left-hand side, there's a couple of things we can simplify. That's 1. And that's 1. Why? Actually, this is 1 also. Right? Everyone remember why those are all 1? Yeah, they're unit vectors, right? So that was the point of that step in the proof. Show that they're unit vectors and you get this nice simplification. All right, great. So now we can subtract a bunch of stuff and we're left with this. 2 times the gradient of D1 times the gradient of D2 is equal to -1. And then we can divide both sides by 2, so we get gradient D1 gradient D2 equals -1/2. So I guess if you have good intuition about dot products and things like that, that might automatically register something in your head. I don't have I don't work with them enough to really have that, but looking at the proof, it ultimately made sense to me. These are vectors. I've actually been a little bit lazy here in the way I wrote the products. Since they're vectors, right, then I really meant a dot product here. Okay. In fact, probably instead of squaring them, what I should have said is dotting them with themselves, really. So dot each with itself. Anyway, point is that this down here is a dot product. That's what I really need. And so you might remember there's another way to write a dot product in terms of magnitude and angle between the vectors. Right? Because where were we headed with all this again? We wanted to find 120-degree angles. So angles have to pop back up at some point before the end of this proof. So what is it here? Magnitude of that times the magnitude of d gradient d2 times, anyone remember, sine, cosine, something else, tangent? Cosine, yeah, good. So cosine of theta, so theta is going to be the angle in between. It should be clear as it comes out of the dot product, but just to make sure everyone's on the same page, theta is the angle between. So D1 and D2, those gradients, so that ends up being AP, right? Because D1 points, remember the gradient D1 points in the direction of AP, and the gradient of D2, we didn't prove it, but by analogy, we could have, that's BP. So that's, again, that's like here, here's A, here's P, here's B, here's theta. Okay. So we're pretty close now. The gradients of these two guys are both 1. We showed that before. So now all we have is that angle has a cosine of negative 1/2. And so if you remember your early trig stuff, oh man, that's like the 60-degree angle where cosine is negative. So that's in quadrant 2. So it's 2 pi over 3 or 120 degrees. Okay? And so that's the end of the proof. Put a little sentence here that just says the angle between the lines connecting the terminal nodes and the Steiner node is 120 degrees. We only showed it for one pair. Obviously, you could repeat the same process to do the same for the other angles, right? I'll red them in, or use some other color here. How about green? All right, so these guys here, so there's C. So this guy's also 120, and this guy's also 120. That's probably clear, you guys. Okay, so that's it for that proof. There are a few more details to it, or follow-ons, like if the angles or greater than 2 pi over 3 in the triangle, something like that. I'm going to skip that. You could look into that if you're interested. Any questions? I think because we're at the hour and 10 or whatever, yeah, hour and 10-minute mark, I'm not going to start anything else now. The other two things to do are the construction, so that might take another 20 minutes. I'll just do that on Tuesday. And I'm also going to show you some Mathematica that I posted on D2L. There's one of the homework questions that you can use the the Mathematica on. Mathematica is pretty straightforward, and it's based on the derivation I just did. So you could start looking at that and figuring that out on your own. I have confidence, but yeah. Otherwise, that's it. So I'll end it there. I'll stick around if people have questions, and yeah, that's it. So have a great weekend. Stay safe, and I'll see you Tuesday.
Hi, doctor.